Hello students, welcome you all. In my previous lecture of alkyl halides, I told you about the difference between nucleophile and base, difference between nucleophilicity and the basicity. Now before starting the nucleophilic substitution reaction, I should also discuss about the leaving groups. So what are these leaving groups? Now this leaving group, suppose I write some of the examples of this nucleophilic substitution reaction. Suppose if I have ethyl alcohol, and this ethyl alcohol, if it reacts with ethyl iodide, then in this reaction, so this is the example of nucleophilic substitution reaction, and here as this iodide ion having this delta negative charge or partial negative charge, and this has the partial positive charge. Now this ethyl alcohol, in this case, it will act as a nucleophile, and the lone pair of electrons, the electron rich part, that will attack on this electron deficient part, and this iodide ion, it will leave out. So what would be formed? You will get the ether. In this case you will get ether plus iodide ion that will leave out. So this iodide ion which is left out, which is leave out, this is called as the leaving group. This is called as the leaving group. This is the nucleophilic product, and this is the nucleophile, and this is our substrate molecule. So this is the substrate molecule, and this is our product, nucleophilic substitution product. In a same way, suppose I have alkoxide ion. Suppose I have the ethoxide ion. So ethoxide ion here, it will act as a nucleophile, and suppose if I have ethyl iodide, then what would be formed here? Again you will get this ether, and this chloride ion will leave out, and this is the one of the leaving group again. This is the leaving group. Okay, so I have written these two reactions. Now which reaction would be the faster reaction? So two reactions are there, two nucleophilic substitution reactions are there. Which reaction would be the faster? So if nucleophile attacks strongly, if nucleophile is the strong nucleophile, then the reaction that would be the faster reaction. Or otherwise the nucleophilic substitution reaction, that depends upon the other factors also, that I will discuss it in my next lecture. Okay, so this rate of this reaction, as I told you, the attack of this nucleophile on this substrate molecule, this is a kinetic one. It is a kinetic concept. Or the nucleophilic reaction, the nucleophilic substitution reaction, is also a kinetic concept. So because we deal it here with the rate of reaction, how fast is the nucleophilic attack. So that's why we can say this is a kinetic concept. So as the nucleophile attack, the one of the group which is leaving out, and that is called as the leaving group. So more stable this leaving group would be. If I am getting the more stable product, if I am getting the more stable leaving group, it means the faster will be the rate of nucleophilic substitution reaction. So the leaving group should be the stable one. So for good nucleophilic substitution product, to get the good nucleophilic substitution product, to get the faster nucleophilic substitution product, we should have the stable leaving group. So this stability of this leaving group, so this is the leaving group. And how we are getting this leaving group? When this iodide ion is leaving out. So how this iodide ion is leaving out? This iodide ion, this iodine is accepting this bond pair of electron, and it is leaving out. So again here also two bond pair electrons are present, and this chloride ion will leave out with these two bond pair of electrons. When it will attack over it, then this chloride ion will leave out with these two bond pair of electrons and it will acquire a negative charge. So how can we define this leaving group? How can we define this leaving group? So leaving groups are the groups which accepts this pair of electron, which accepts the electron pair when this bond is broken out. So when the bond is broken out between this chlorine atom and this neighboring atom, in that case the leaving group that would be generated. So leaving groups are the groups or species group which accepts this pair of electron, accepts the pair of electron when this bond is broken, when the bond is broken between this chlorine atom and the neighboring group. So when the bond is broken between it means here either this chloride ion, either chlorine or this iodine, and the neighboring group and the neighboring atom, and the neighboring atom is here the chlorine atom and the neighboring atom. So this is in this way we can define this leaving group. Okay, so what I told you, better is the leaving group or better is the stability of this leaving group, then faster will be the nucleophilic substitution reaction. So one of the points that we can write here, that the stable is the leaving group. When the leaving group would be stable, when this negative charge on the group is stable, or we can say when this lone pairs of electron are stable, when the lone pair of electron or the negative charge present on this atom that would be stable, then leaving group will be the stable one. So stable is we can write stable is the lone pair of electron or negative charge then stable will be the leaving group. Stable will be the leaving group. Okay, so the rate of nucleophilic substitution reaction, it depends upon the stability of leaving group, and the stability of leaving group, it depends upon the stability of this lone pair of electron, or it depends upon the negative charge which is present on this leaving group. Okay, so another thing that we can say, that now if we compare this nucleophilic substitution reaction with the acid-base reaction, though this is not the acid-base reaction, this is the nucleophilic substitution reaction. So nucleophilic substitution reaction, as I told you, it depends upon this rate, it depends upon the kinetic factor, whereas the acid-base reaction is the thermodynamic concept. The acid-base reaction is a thermodynamic concept. Now suppose I write one of the acid-base reaction. Suppose I am writing one of the acid-base reaction, and suppose I am suppose if I have hydrogen iodide. Suppose if I have hydrogen iodide and it reacts with water molecule. It reacts with a water molecule, and then what will happen? So here this iodide ion will leave out, or what we can say, the lone pair of electron which are present on this water molecule or oxygen atom, it will abstract this H plus ion, and this iodide ion, this will leave out with its pair of bond pair electron. So what would be formed here? So this will give you the H3O plus. This will give you the H3O plus, and plus this iodide ion, this will leave out. This iodide ion will leave out. Okay, so this is the acid-base reaction. And here this iodide ion, hydrogen iodide being the stronger acid, this is a strong acid, and this strong acid is giving the conjugate base. Strong acid after losing the H plus, strong acid after losing the H plus gives the conjugate base. So this is the conjugate base. Similarly, base after accepting the proton gives the conjugate acid. So H3O plus is the conjugate acid which is formed when the base accepts this proton. So base when accepts the proton gives the conjugate acid, whereas the acid when loses the proton gives the conjugate base. Okay, so the stability of this conjugate base, it depends upon the negative charge. It depends upon the charge which is present over this iodide ion. So stability of this iodide ion depends upon the charge which is present over. So if this charge is neutralized easily, then we say this conjugate base is the stable one. If this negative charge is not easily neutralized, then we can say that this conjugate base which is formed is not stable. So if this is stable, then the base which is formed, that would be the weaker base. So here this iodide ion, if this charge is neutralized, then no doubt it would be the weaker base. So strong acid, it forms the weaker conjugate. More is the stronger acid. Stronger the acid, weaker will be the conjugate base. So from the reaction is going from strong to this weak. Okay, so stronger the acid, weaker will be the conjugate base. If conjugate base is weak, it means the base is stable one. It means the base is the stable one. So if we compare this acid-base reaction with this nucleophilic substitution reaction, we compare with these two reactions, though this is not the acid-base reaction, but if we compare this nucleophilic substitution reaction with the acid-base reaction, then we can say that this iodide ion is one of the weaker conjugate base, because it is accepting the iodide ion is formed after accepting the pair of electron. In the same way, this here iodide ion is also formed after accepting the pair of electron. So that's why what we can say that this leaving group is a conjugate base. Leaving group acts as a conjugate base. So what I told you, if conjugate base is a stable one, then that should be the weaker. And no doubt this iodide ion which is formed, that should be the stable. And if it is stable, it means this is a weaker conjugate base. So for good nucleophilic substitution reaction, for faster nucleophilic substitution reaction, the leaving group that should be formed, that should be the stable, or we can say that should be the stable conjugate base, or we can say that should be the weaker conjugate base, because stable is the conjugate base, weaker it would be. So another that rule that we can write, very important rule that I can write, that the leaving groups, weaker is the one of the things, the leaving groups are the conjugate base, or weaker is the conjugate base. Weaker is the leaving group, or we can say, because it is a conjugate base, weaker is the conjugate base. Okay, weaker is the conjugate base. Better, weaker is the conjugate base. Better is the leaving group. So we can indirectly we can say that leaving groups are the weaker conjugate base. Okay, so leaving group should be the weaker conjugate base. Then only the nucleophilic substitution reaction, that would be the good nucleophilic substitution reaction. That would be the faster one. Okay, so how can we determine the whether this conjugate base that is formed is a weak or strong? So here the strength of this conjugate base, that can be determined for this particular acid-base reaction. The strength of conjugate base can be determined by the Ka value, or we can say indirectly we can say pKa value. So the strength of this conjugate base can be determined by the pK value. And how we can determine the Ka value? First we determine the pK value, and then we can determine the pK value. That is, pK is equal to negative log of this the concentration of this, that is negative log of this Ka. So Ka is the concentration of this multiplied by concentration of this divided by concentration of this multiplied by concentration of this, like this. Okay, so we can determine the pKa value for any conjugate base, or we can say that pKa, it tells about the strength of acid and base. pKa chart, it tells about the strength of acid and base. So let's see one of the pKa chart. Suppose I am writing one of the pKa chart. Suppose this is your acid, and it's a pKa value, and when acid loses the proton, it forms the conjugate base. So acid gives the conjugate base. So suppose if I write this iodine or hydrogen iodide. So for this hydrogen iodide, the pK value, if I write this acid-base reaction for this hydrogen iodide, then this pKa value is found out to be -11. Okay, so and what would be the conjugate base formed? Iodide ion. In the same way, if I write hydrogen bromide, then pK value is -9 and bromide ion is this one. And the same way, if I write HCl, then it is -7, chloride ion is formed. And if I write the para-toluene sulfonic acid, and then this is para-toluene sulfonic acid. So for this para-toluene sulfonic acid, that this pKa value, so this is -11, this should be the, I think, -7, it should be -5, and this is -3, and this is para-toluene sulfonic acid, or PTSA, or we can write the PTSA. So this, after losing this proton, it will form the para-toluene sulfonate. Okay, so this is also called as the toluic acid, or this is the para-toluene sulfonate group. Okay, so OTS, or we can say, and this is the OTS group. We can write this OTS group also. Okay, so now in the same way, if I write H3O plus, it has a -2 pKa value, and when this H3O plus lose the proton, what would be formed? H2O. In the same way, if H2O having this 15.7 plus 15.7 pK value, and after losing the proton, it forms OH minus. In the same way, if I have suppose sodium methoxide or this ethyl alcohol. Ethyl alcohol. So this ethyl alcohol, after this losing the proton, what it will form the ethoxide ion. It will form the ethoxide ion, and for this one the pKa value is plus 16. Now if you will see this pKa chart, if you see this pKa chart, then weaker is the conjugate base, stronger will be the better will be the leaving group. So in this case, this conjugate base, this iodide ion is the weakest conjugate base. It is the weakest and conjugate base. This is the weakest conjugate base, and it is the stable leaving group, most stable leaving group. Whereas this ethoxide ion is the strongest conjugate base. This is the strongest conjugate base, and this is the least stable leaving group. This is the least stable leaving group. It will not leave out easily. This ethoxide ion will not leave out easily, whereas this iodide ion can easily leave out. So that's why it is a better leaving group. It is the most stable leaving group. Okay, so if we see, then in nucleophilic substitution reaction, suppose I have the substrate molecule. I took this in example. What I took, this was the substrate molecule, and I reacted with one of the nucleophile, that was the suppose ethyl alcohol, and what was formed? Ether was formed. The ether was formed here, and iodide ion was the leaving group. So here better is the leaving group, or weaker is the conjugate base, better will be the leaving group. So it can leave out easily, because one of the thing that here this negative charge is much more delocalized over the big iodide ion. Negative charge is much more delocalized over the big iodide ion. That's why this iodide ion, the negative charge is much more stable over this iodide ion in comparison to the bromide, in comparison to the chloride. So iodide ion being the big in size, the negative charge is much more delocalized over it. That's why it is much more stable. So that's why it is much more stable. So if you see, if we compare with it with the these different leaving groups, if we compare with this different leaving group, then this is the weakest. This is the weakest leaving group. This is the weakest or least stable leaving group. Whereas the OH minus is the OH minus is also a weak leaving group. OH minus is also a less stable leaving group. So this is one of the reasons, as we can say, OH minus is the least, one of the least leaving group. That's why in nucleophilic substitution reaction, the ethyl means alcohols are not easily substituted by the nucleophile. So why the alcohols cannot be easily substituted by the nucleophile? Because it cannot be easily substituted by any nucleophile. If I take any nucleophile, then it cannot easily be substituted. This reaction will not occur. So why this reaction will not occur? This reaction will not occur because this OH minus is the very weak leaving group. OH minus is the very weak leaving group. That's why it will not leave out. This reaction is not possible. The nucleophilic substitution reaction is not possible in case of alcohol easily. But we can do the nucleophilic substitution reaction in acidic condition. So that I am writing here one of the nucleophilic substitution reaction in alcohol in presence of some acidic condition. So weaker is the leaving group, stronger will be the nucleophile. So this it can act as strong nucleophile. As I told, this ethoxide ion can act as a good nucleophile. In the same way, ethyl alcohol can act as a good nucleophile. So weaker is the leaving group, stronger will be the nucleophile. So this is the strong nucleophile. What we can say, this acts as a strong nucleophile, whereas this acts as a weak nucleophile. It acts as a weak nucleophile. Okay, so this can so the leaving group can easily be understood by or we can say stability of leaving group can easily be understood by this pKa chart. So what I told you, this hydroxide ion is a weak leaving group. That's why the nucleophilic substitution reaction is not possible. But it is possible. It can occur in presence of some acidic condition or some other reaction like SNI reaction. In SNI reaction, the nucleophilic substitution reaction in alcohols are possible, which occur in presence of thionyl chloride. So, or otherwise it can occur in presence of some catalyst. Suppose I write here okay, so if I substitute with any nucleophile, then in this reaction will not be possible directly. But once if I add any acid catalyst, then what will happen? Here this acidification of that will occur, and now this will leave out. Now in this case it will leave out, so this will not leave out. So this will leave out and it will give the positive charge over here, and now any nucleophile can be added over this carbocation. So this is possible in presence of some some catalyst, otherwise it is not possible. So this is about the leaving group. Now in my next lecture I will discuss about the nucleophilic substitution reaction, where I will start the SN1 reaction. Okay, thank you.